All right, so here's number 57. We got this block here, this mass M has been pushed into this spring, right? This block has been pushed into the spring. We know the spring constant of the spring. So let's see, so this K right here, K, spring constant of the spring is 78.4 newtons per meter. The spring is released and it shoots this mass, okay? The mass goes across this horizontal surface and then up through the loop like that, right? Everything is frictionless except, the problem tells us, everything is frictionless except this region from A to B, okay? There's friction between A and B. What this problem wants us to solve, oh, and they give us the coefficient of friction. The coefficient of friction is 0.3. This mass right here is 0.5. So we have the mass of the block, we got the spring constant. Oh, we have this radius. The radius of the loop is, where is it? 1.5. 1.5 meters. And the question is this: what is the minimum distance the spring has to be compressed so that the block barely makes it through the loop, right? Because what happens if the block goes too slow through the loop? It'll fall out. It'll go and fall out, right? So we're looking for the minimum distance d that the spring needs to be compressed so that the block makes it through the loop. Does that make sense? Now, where does this problem begin? Does this problem begin down here at the spring? No, you got to start the problem up here, right? At the very top of the loop. You got to first find the minimum velocity at the top of the loop, which we've done before. So look, how do you find the minimum velocity that the block must have at the top of the loop? Well, you go, okay, free body diagram. As the block passes through the highest point of the loop, what are the forces on this block? You got two of them. You got mg, and then what else do you have? Normal force. They're both pointing down to the center. For circular motion problems, make the center of the circle positive, because that's where the centripetal acceleration points. So you sum the forces. So we have normal force to the center and mg to the center. They're both positive. Sum of the forces always equals ma. Now, what type of A is that? It's a centripetal. How do I know it's centripetal? Because it's in a circle. So centripetal acceleration has an equation. It's equal to v squared over r. Okay? Now, the key idea for finding minimum velocity at the top of the loop, if the block is at its minimum velocity, that means it's on the verge of losing contact with the track. So what do we do to the normal force? Set the normal force to 0. You're left with this. The m's cancel, and you get v equals square root gr. So plug in the values, right? G is 9.8, r is 1.5. So we find out the minimum velocity is 3.83. That's v min. Now, we're almost done. Well, halfway done. So now, how do we find this d here? We're looking for the minimum distance the spring had to have been compressed. So now that we know the velocity at the top of the track, how do we figure this out? What concept? Conservation of energy. We're going to use conservation of energy. So let me revert this back. Okay, so we now know the velocity there is 3.83. That's the minimum. What else do we have? Got the spring constant. Ooh, there's friction from A to B. Now look, this is the initial. This dot is the initial. This is the final. Okay? What type of energy do we start with over here? Potential of spring. That's it. No other energy. Okay? Now what happens in this region here? We lose energy due to friction, work of friction. And then up here, what type of energy do we end with? We end with potential of gravity plus kinetic. Okay? So here's the idea using conservation of energy. So potential energy of spring initial, right, down here, minus the work that friction does, right? Friction's going to steal energy, is going to equal this. It's going to equal potential of gravity final plus kinetic final. All right, so then you plug in your equations. So potential of spring, 1/2 k d squared, right? D is what they're calling it. Okay, what's work of friction? What can we say about work of friction? What's the equation for work? Force times distance. Okay, so what's this x going to be? That x is 2.5. They give that to us. The distance from there to there, that's 2.5 meters. They give that to you. Okay, equals mg. Now, what's the height up here? 2r. It's double the radius of the loop. Plus 1/2 mv squared, where we already solved for that. That v right there is the 3.83. Okay, this x is the 2.5. Okay, and then friction. Guys, you got to solve for friction. What's the equation for friction? Mu times normal force. In this case, what's the normal force? If you look at the block when it's down here, look. If you look at the block when it's there, you got mg down, you got normal force up. What must be true about normal force and mg? They're equal. So friction comes out to be 1.47 newtons. That should be 1.47. Now look, we have everything. If you look at that equation, we got everything except what? D. Take that, solve it for D. And I'll be honest with you, I don't know what the answer is, but I pretty much solved it for you, everything except punching it into the calculator. So you got R is 1.5, you got M, you got everything. Just solve that for D.